We'll start by looking at the generic rules. So the derivative of the exponential function, we took a look at this before. The derivative of e to the x is just e to the x. And with the chain rule, we can extend that to say if I have the derivative of e to the g of x, so now g of x is inside of e to the x, well, the derivative of the outside, e to the x, is just e to the x, and we leave the inside the same, so that's e to the g of x. And then, of course, we multiply by the derivative of the inside, and the inside is g of x, so the derivative of that is g prime of x. So this is really just an application of the chain rule written out as a specific formula. But what we haven't gone over yet is what happens if I want the derivative of a general exponential function. So let's say I'm trying to differentiate with respect to x b to the x, where b is some positive number. The derivative of b to the x is going to be natural log of b, so natural log of the number b times b to the x. And now what I want to show you is how this generic exponential function derivative rule is how this formula came about. So the derivative of e to the x, well, remember that e is just a number, so by this rule, I would have the natural log of e times e to the x. But let's remember that the natural log and e are inverses, and this is an e to the 1, so these essentially become just a 1. So it's 1 times e to the x, which is just e to the x. So that's why the derivative of e to the x is e to the x. It's coming from this derivative for general exponential functions rule. So if this is any other number besides e, we're going to have natural log of that number times b to the x. And we can, of course, extend this using the chain rule. So if I have b to the g of x, I'm going to have b to the g of x times that natural log of b, and then times the derivative of the inside, g prime of x. So now let's go ahead and see these in some examples. All right, let's take a look at these 4 examples. So here we're asked to find the derivative of y equals 4 to the x. So the first thing I want to point out here is that this is not a power rule. The power rule says that I need a variable in the base and a number in the exponent. And in fact, I have the exact opposite. I have a number in the base and a variable in the exponent. So this is the derivative of a general exponential. So y prime is going to be the natural log of the base. So the base is 4, the natural log of the base, times b, the base was 4, to the x. So that's it. It's really just a matter of remembering the rule. So we'll go ahead and jump down and find the derivative of y equals 3 to the sine x. So this is a case of having a number in the base and a function of x in the exponent. So I'm going to have to apply the chain rule or use the extended version of the derivative of a general exponential. So the outside function is 3 to the x. So instead of 3 to the x, though, I put 3 to the sine x. I leave the inside the same. And part of that derivative involves natural log of the base, and the base was 3, so natural log of 3. But then the remainder of the chain rule says that I need to multiply by the derivative of sine x, which is cosine x. And I want to point out here that this is multiplicative, so it can go in any order. So if I want to, I can put the natural log of 3 in front, I can put the cosine x after it, and then 3 to the sine x. And just make sure that everything is in line with where it's supposed to be. So in other words, the sine x needs to be clearly in the exponent. Cosine x is not in the exponent. It is just being multiplied to the entire thing, so it needs to be on the same level. I don't know another way to say it. So on that same level as natural log of 3 and the 3 here, but sine x is in the exponent. So this whole big weird looking thing is my derivative. And so now let's go ahead and practice with just the exponential function e to the x, or in this case, e to the tangent x. So if I take the derivative of this, well, I'm going to have just e to the tangent x, and then times the derivative of tangent x is secant squared x. And I'm just going to go ahead and put that in the front. So that's just applying the rule, and I'll write it below. If I have e to the f of x, it's going to be f prime of x times e to the f of x. So I just basically repeat the whole entire function. So you'll see there's e to the tan x, there's e to the tan x, and then the derivative piece, I mean, it doesn't have to go in front, but I went ahead and followed the rule that we saw previously where the derivative goes in front. So this is my solution. Secant squared x times e to the tangent x. And then one more example, we're changing the variable here to mix things up a little bit. I have the derivative with respect to t of e to the 2 minus t. So I have another case of e to some function. So I'm just going to repeat the whole thing. If I have e to some function, it's that exact same thing, e to the 2 minus t, but then I have to multiply by, and typically in the front, the derivative of what was in the exponent. So the derivative of 2 minus t, well, the derivative of 2 is 0, and the derivative of minus t with respect to t is that negative 1. And so I will rewrite this as negative e to the 2 minus t. So this is my derivative. Now we're going to extend our rules for derivatives and look at the derivatives for logarithms, and we'll start with the derivative of the natural logarithm. So the derivative with respect to x of the natural log of x, so specifically ln x, is 1 over x for any x values that are greater than 0. And that's because the natural log function is only defined for x values greater than 0. That's its domain. So the derivative also only applies to values in the domain of x. So we can extend that a little bit to the derivative of the natural log of g of x. So this is an application of the chain rule. We're just generalizing this formula. So if I have the natural log of g of x, so instead of just x, it's a function of x, well, that g of x is going to go to the denominator of a fraction. So notice we took the inside piece and it goes to the bottom. So just like here, the natural log x, that inside piece, that x, went to the bottom. And what goes on the top is the derivative, g prime of x. And here you can see, well, the derivative of x is just 1. So we have that parallel happening, and this is, again, just an application of the chain rule for now the natural log function. So when I see the derivative of the natural log of some function of x, I take the inside and I put it in the denominator, and the derivative of that goes in the numerator. And now to extend that to general logarithms, so natural logs is a special type of logarithm with base e. Now if I have the derivative of a general logarithm, so I have log base b of x, that's going to become 1 over x, but now you see in the denominator we have the natural log of b. So whatever the base was, we have natural log of b now in the denominator as well, next to the x. And what I want to show you here is where this formula is coming from, the natural log formula. It's an extension of the general logarithms derivative formula, because natural log, so the derivative of ln x, that's the derivative of log base e of x. Well, that's 1 over the natural log of e. So I'm replacing the base b with e, because natural log is base e, so ln e times x. And as we looked at before, natural log and e are inverses, so this becomes just 1, so it's 1 over x. That's where this formula is coming from. It's a specific case of the derivative of the general logarithm. And then once again, we're going to go ahead and extend using the chain rule. So if I have the derivative of log base b of g of x, so now the inside goes in the denominator, g of x goes on the bottom, g prime of x goes in the numerator, and because I have a base b, ln b goes in the denominator multiplied times g of x. So for all of these, we're assuming that x is greater than 0 because logarithms are only defined for positive numbers. Now we'll go ahead and take a look at some examples. Find the derivative of y equals the natural log of x squared plus 3. So this would be the application of the chain rule. So I have natural log of x squared plus 3, and our nice rule says that I take the inside of the natural log piece and I put it where the x would normally be in the derivative of natural log of x. So that x would go on the bottom, so now instead of that it's the inside, so x squared plus 3. And then the derivative of that inside, well, normally we multiply by the derivative of the inside, but instead of putting the derivative over here to the right, we're going to put the derivative in the numerator. So the derivative of x squared plus 3 is just 2x plus 0, of course. So 2x over x squared plus 3. And this cannot be simplified. I want to clarify these x's do not cancel because I have this addition here. So this is my final answer. Let's go ahead and work down. I'm taking the derivative of y equals log base 2 of x cubed. So again, this is a derivative that involves the chain rule application. So I have a general logarithm, the base is 2, and the inside function is x cubed. So the derivative y prime is going to be, well, I take the inside function and I put it on the bottom. So whether it's a natural log or a log base 2, whatever that inside function is, goes in the denominator. The derivative of that piece goes in the numerator, so the derivative of x cubed is 3x squared. But because this was a log base 2, the natural log of 2 goes in the denominator as well. And now, since this problem is all multiplication and division, I can simplify. So this x squared will cancel with 2 copies of the x squared down here and leave that as an x to the 1. So my simplified answer would be 3 over, I'm going to put x times the natural log of 2. So maybe you might be asking, well, why did I put the x in the front? The reason I did that is because sometimes students might leave it as 3 over ln 2x and not be clear that ln 2 needs to be in parentheses, and if it's not, it looks like that x is connected to the 2, which would make it incorrect. So that's why I put the x in the front, to make that clear. Alright, so now we'll go ahead and look at the next example. I have the derivative with respect to k, so now we're saying that the variable is k, of the natural log of 1 over k squared. So the first thing I'm going to do is rewrite the inside. I'm going to rewrite 1 over k as k to the negative 2. And the reason for that is because my derivative rule for natural log of a function says I take that inside function and I put it in the denominator. So I'm going to put k to the negative 2 in the denominator and the derivative of k to the negative 2 in the numerator. So the derivative by the power rule is negative 2k to the negative 3, right? I subtract 1 from negative 2, which is a negative 3. And now I want to simplify this. So the negative 2 stays in the numerator. So that's negative 2 times k to the negative 3. The only thing attached to the negative 3 is the k. And negative exponents means I take that term, just that k to the negative 3, move it to the bottom, make it k to the positive 3. And this k to the negative 2 moves to the top and becomes k squared. And now again, since everything is being multiplied or divided, this k squared will cancel with 2 copies there and leave just 1 copy on the bottom. So negative 2 over k is my derivative after simplification. And then finally, let's take a look at the derivative with respect to x of log base 10 of cosine x. So one of the things I wanted to point out is that this 10 really doesn't need to be here. If the problem just said the derivative with respect to x of log of cosine x, that's actually the same problem because that's called the common log. When there's no base explicitly written here, it's assumed that it's 10. So let's assume that it was this problem just for that practice on logarithms, and this would be the chain rule. So I take the inside and I put it in the denominator, and then the derivative of the inside goes in the numerator. So the derivative of cosine is negative sine x, and then in the denominator, I have to multiply by natural log of the base. And so if the base wasn't clearly written for us as a 10, we would just have to know that. We would have to know that we needed to put natural log of 10. And so we can leave our answer like this, but one of the other things that we can do is we can simplify this to be -1 over natural log 10, and then hopefully you're following what I'm going to do to simplify this. Sine x over cosine x is, hopefully you said it, tangent x. So this could potentially be a multiple choice question, and if you didn't see this as the answer in terms of sines and cosines, it might be because you're expected to recognize those quotient identities for trig functions, that sine over cosine is tangent. Alright, now we're going to look at some AP practice that involves exponentials and logs derivatives. So in this one, I have f of x equals e to the 2x over 2x, so divided by 2x. Then f prime of x equals, so I'm being asked to find the derivative, and I have a quotient. Now, whenever I have a quotient, I can definitely use the quotient rule. I want to sometimes see if it's worth it to do any simplifying first to avoid the quotient rule, but in this case, I want to take a quick glance at my answers, and one of the things I want to notice is that the answers all look like quotients. So I'm probably not going to get out of doing the quotient rule here. That's the strategy that I want to use, so I'm not going to rewrite it using any algebra first. I'm just going to jump straight into the quotient rule. So the quotient rule says logₐ, so log 2x, dₐ, so the derivative of the numerator is a chain rule involving exponentials. So the derivative of e to the 2x, well, we just repeat it, right? E to the 2x times the derivative of the inside, so the derivative of 2x is 2. So logₐ minus high e to the 2x, d log, so the derivative of 2x is just 2, and then all over the bottom squared. So log squared, the quantity 2x squared. And one of the things I want to direct your attention to is where all the parentheses are. So around each term, whether it was low and then the derivative of high, each term I kept inside of parentheses. Even if it was just the number 2, I kept it inside of parentheses, because the problems that come after the initial quotient rule are simplifying, and those are some of the biggest mistakes that happen. So here, now after I have everything in parentheses, I'm going to attempt to simplify. So one of the things I want to point out, and please, please, please don't do this, is that this 2x and this 2x do not cancel. So this is one whole term on the left, and this is one whole term on the right, and they are separated by subtraction. So I know maybe you're thinking, well, these two are multiplied, so I can cancel this 2x and this 2x. You cannot, because it's part of a bigger term that is subtracted from this term over here, and so I can't cancel the 2x's. Not possible. So what I can do is I can recognize that both terms, so this whole thing, use a different color, this whole thing is one term, and this whole thing is another term, and so everything in this whole term is being multiplied, and everything in this whole term is being multiplied. So what I can do is I can factor out what's common in each of these two terms, these things underlined. So if I want, I can pull out a 2, so I'm going to do that because I'm trying to simplify, because there's a 2 here and a 2 here that's multiplied. And they also each have an e to the 2x. So I'm going to pull out the e to the 2x. And then what's left over? Well, let's say I pulled out this 2 right here. There's still another 2. And there's an x. So there's a 2x minus. And then over here, I pulled out the 2 and I pulled out the e to the 2x. So what's left is a 1. So hopefully you weren't thinking out loud 0, because nothing's left. A lot of people think, well, nothing's left, but multiplicatively there's a 1 left over. So I'm going to go ahead and keep that all together, and then all over, now the bottom is the quantity 2x squared, and so since this is multiplied, the squared applies to both, so it's going to be 4x squared. Alright, so now I have 2e to the 2x times this whole quantity, 2x minus 1, over 4x squared. So let's see, do I have one that matches that? Pretty close, e. It's just that I have to cancel the 2 and the 4. This 4 will become a 2. Now, why can I do that? Because everything was multiplied. So I know this is subtracted, but this is like one whole thing. So I'm going to rewrite it as 2e to the 2x times 2x minus 1 all over 2x squared. Oh, I'm sorry, 4x squared. So that is why I can cancel, is because now I have multiplication between everything. So 2 times e to the 2x, and then 2x minus 1 is one whole thing in parentheses. So that's the only reason I can cancel this out to become a 2 and say that it matches the answer E. Now we'll look at two more AP level questions. So if y equals 10 to the power of the quantity x squared minus 1, then what is the derivative of y with respect to x? So this is just a straightforward application of our rule. So I have a general exponential, so I'm going to have that entire term repeated. So I'm going to have 10 to the x squared minus 1. And then because the base was 10, I'm going to have a natural log 10 involved. And because it was an entire function of x here, I'm going to multiply by the derivative of what was in that inside, in that exponent, and the derivative of that is 2x. So now we just need to look for which one matches that, which is option D. So we have 2x, natural log 10, 10 to the x squared minus 1. And I also want to just point your attention to the fact that I was not tempted to look at my answer choices, because if you forgot that rule, you might just jump down and say, oh, it needed a natural log 10, and that answer is going to fake you out, whereas it needed the chain rule. So make sure that you attempt to solve the problem on your own before you attempt to look at the answer choices, of which 4 are incorrect. And now this next one, if f of x equals sine of e to the power of negative x, then what is its derivative, f prime of x? And this is actually going to be two chain rules. So negative x is inside of e to the x, and e to the negative x is inside sine x. So the outermost function is sine, and the derivative of sine is cosine. And then we're going to leave the inside the same. So cosine of e to the negative x times, and then remember what goes here is the derivative of e to the negative x, which is its own chain rule, because this is a negative x here, right? It's not just an x. So this derivative is not just e to the negative x, it's e to the negative x times negative 1. I have to remember that the derivative of this exponent has to be included, which is just a negative 1. So now it's negative e to the negative x, and then cosine of e to the negative x. And let's go ahead and see which one of those I match up with, and that is option E. Lots of E's. So this is it for our answer. One of the other things I wanted to point out, they could have rewritten it so that e to the negative x, just this piece right here, was written in the denominator, was another option. One of the things that is not an option, let's remember, is we can't ever take anything and put it into a trig function or have anything inside come out. So this is the only way our answer could have been written, which is why that is one of the options as the correct answer for this problem. Alright, for these next three problems, I really wanted these next to each other to show the different rules and simplifications that we can and cannot apply. So for this first one, I have f of x equals the natural log of this entire quantity, x plus 4 plus e to the negative 3x. And I'm being asked to find the derivative at x equals 0. So remember that we can't just plug in 0 first, we have to take the derivative first. So the derivative, f prime of x, is going to be taking the entire inside, so this is natural log, so anytime I have any type of log, the entire inside goes in the denominator, x plus 4 plus e to the negative 3x, and then the derivative of this goes in the numerator. So the derivative of x is 1, the derivative of a constant 4 is 0, and the derivative of e to the negative 3x requires the chain rule, so plus e to the negative 3x, and then times the derivative of the inside, which is the derivative of what's in the exponent of this exponential is a -3. So this is my derivative function. Nothing about it can be simplified, so I have all of this addition happening here and subtraction on the top. So I cannot cancel these e to the -3x's at all. And what I want to do at this point is substitute in my 0 now that I found the derivative. So f prime of 0 is 1 minus, so I'm just plus a negative is minus, and then 3e to the 0, right? So that whole thing will become a 0. And then I have 0 plus 4 plus e to the 0, right? Because this exponent will become a 0. So I have 1 minus 3, because anything to the 0 is 1. So remember that this is 3 times e to the 0. So the only thing becoming a 1 is e to the 0, right? The 3 doesn't go away. Sometimes that happens with some students. Then this is 0 plus 4. So 4 plus, again, e to the 0 is 1. So I have -2 over 5. And yay us, that is an option. It is A is the answer to this first one. Now, for the second one we're going to look at, the derivative with respect to x of natural log of e to the 2x. So here, what I want to point out is that what we're trying to differentiate, the natural log of e to the 2x, can be simplified. So the derivative with respect to x, instead of taking the natural log of e to the 2x, I want you to think about it before I say it, will become just 2x. And the reason for that is because natural log and e to the x are inverses, so they will just become what's in the exponent here because they are right next to each other. I have natural log of e to the 2x, and so that just becomes 2x, and the derivative of 2x is just 2. And I'm laughing at myself here because you can see 22 is a little bit like blown up, and I lost the other answer choices. So the answer is 2. Let's just say that was option D, because that's what we're trying to focus on, is just understanding that when we have natural log and e involved in a function, sometimes it could be simplified first to make our life easier for differentiating. So in this case, the answer would just be 2. Now I want to draw your attention back up to the previous one for a second, because sometimes people see this natural log and this e to the -3x way over here and somehow think that they cancel, and they don't. So I'm not entirely sure how. I can understand, hopefully, that you know that ln and e have something to do with each other. They're inverses, but there's very specific ways they need to be in order for them to cancel, quote unquote, right? So it's because they're inverses that composition is making them in this example, yield just that 2x, right? And it's not a 2x just like up in the exponent. So it's another crazy thing I see happen is sometimes people say, oh, this is d dx of like 2x, and they keep 2x up in the tiny corner like it is up here. And that's not true either. That doesn't make any sense at all. So it's the derivative with respect to x of 2x. Like it actually becomes no longer an exponent anymore. So it's just the derivative of 2x, and then we still have to take the derivative of that, which is 2. So now, with that in mind, let's look at the last one on this section. If f of x equals e to the 3 times natural log of x squared, then what is f prime of x? So here, I have e to the 3 times natural log of x squared, and a lot of students end up canceling this e and canceling this natural log, and it doesn't work. So e and ln are absolutely inverses, and in order for us to do any type of canceling or use of the fact that they're inverses would require this 3 not be there anymore. So I cannot have this 3 in the way. I have to move it, and the way I'm going to move it is I'm going to recognize that this 3 is in front of a logarithm, and my properties of logs say that I can take this 3 and make it an exponent of the argument, which is x squared. So here's what I'm going to do. I'm going to rewrite f of x as e to the natural log of x squared cubed. So I took that 3 and I made it an exponent of the argument. Well, the argument already was x squared, so now it's x squared cubed. So this is now e to the natural log of x to the 6th. So my properties of exponents say this becomes x to the 6th. And now e and natural logs relationship as inverses says that this becomes x to the 6th. So the function I was actually given was the nice function x to the 6th, the power function x to the 6th. So now to take the derivative of this, just the power rule, 6x to the 5th, which is option E. So I wanted to have these next to each other to show when I can and when I can't use the relationship that natural log and E have, that inverse relationship that allows us to simplify and make our lives a little easier, but sometimes people just want to use it all the time when it can't be used. And so notice on these multiple choice questions, there's a lot of past knowledge that you need, those relationships, these exponents. So sometimes students might say this is x to the 5th, and then notice what the fake out answer is, 5x to the 4th. And that's because some students will add these together instead of multiply them, and then they have that fake out answer here of 5x to the 4th for those students who don't know that property. Which is frustrating because you've already done so much, and to not know your algebra skills and get this question wrong is not worth it. So make sure that you go back and learn those rules. Alright, final AP style question comes from the free response portion. So this was one part of a question on free response. We're told the amount of coffee in the cup in ounces is modeled by B of t equals 16 minus 16e to the negative 0.4t. Using this model, find the rate at which the amount of coffee in the cup is changing when t equals 5. So here, I'm being asked to find the rate, which means I want to find the derivative. I want the rate when t is 5 at a particular instant. So I'm being asked for the instantaneous rate of change, which is the derivative. Right? So the derivative, slope of a tangent line, limit of a difference quotient, and instantaneous rate of change. So I'm being asked to find the derivative of this function b of t, because this function is the amount of coffee in the cup, and I want the rate at which the coffee in the cup is changing. So I want b prime of 5. So remember that I have to take the derivative before I plug in 5. So I want b prime of t. So these two terms are separated by subtraction. The derivative of 16 is 0. And now let's look at this piece. What is the derivative of this piece? So this constant in the front, negative 16, can just stay there. And the derivative of e to the negative 0.4t, well, the derivative of e to some function just stays that exact same thing, right? So e to the negative 0.4t, and then we multiply by the derivative of that function in the exponent. And the derivative of negative 0.4t is just negative 0.4. Kind of going to have to cram that into the little space I left myself, but it's just negative 0.4. So imagine if it was just, what's the derivative with respect to x of e to the 3x? So that's just, well, e to the 3x times 3. It's not any different given that it's this decimal, or this negative decimal for that matter. So we really kind of have to get used to seeing some weird numbers and different variables, different names of functions. And because this is free response, we would not need to simplify it. So we could leave our answer like this, negative 16 times the quantity, negative, again, that's 0.4, e to the negative 0.4t. Oh, and we're not done, actually. We have to plug in the 5, and then we're done. So it'd be negative 16 times negative 0.4, and then e to the negative 0.4 times 5. And then we can leave it like that. So I got ahead of myself there. I was asked to find the derivative at 5, the rate at 5, so I just plug in my number, make sure I have, the right amount of parentheses everywhere, and that is my answer.